So I've got this model, and I have only done, when you talk about verification validation, so I've done one part to is stairs, which has been published previously. If you go into the SFP handbook, there's an example of a 9-story building, and they give you a hand calculation for the time it takes for everyone to get out. So I basically tried modelling that same 9-story building in the network model, and you basically get the results you get here, which are shown here. So the SFP handbook, hand calc says it's 15 to 1,524 seconds. If I put it in my model, I get 1,506 to 1,522, a range because of the Monte Carlo aspects, which is pretty close, I think. And the other thing I was checking against was there's some classic work by Jake Pauls, and he comes up with basically a one-line equation for how long it takes for people to exit a building. And this is Jake Pauls' plot here. So the three results: the SFP handbook, my network model, which basically codes up the SFP handbook equations, and the Pauls model. And I kind of argue in this previous work this works well. And again, whether this debate about what works well or not, it's within N% of the model of the hand count. But clearly, this is not real data. This is a hand count which has been written up in the SFP handbook, but we don't know whether the hand count is right or wrong. All we can say is, well, if you compare it to Pauls, which is based on data, the results, are comparable. Somewhat, you might say, a little bit more conservative. But when you look at Paul's work, there's actually quite a spread of results as well. He's put a sort of best fit line through it. So that's okay. We've got this stuff from stairs. But what's been happening recently is in parallel to what Garth's been doing and the data that he's got from Hamish McLennan, the guys at NIST have been collecting some stairwell evacuations in various buildings around the US for the last sort of year or two. So, and they put this stuff on the website. So I thought, this is great. Now I've got some real data, you might say real data, to allow me to compare the network model with timings that are taken from these buildings. As you see here, there's a range of buildings in terms of their height, from 10 to 62 stories, a number of stairs that they've monitored, and each one of these just shows the number of people. So some relatively high numbers of people, 600, 700 people, and then some lower numbers. And then they've got some information about the time it took, the total time for people to evacuate, and also some information about what we might call here the stair entry delay. So what they've been, these are trial evacuations, yes, they're not. And some are compulsory, some are voluntary, some are, so there's a little bit, some information in some stuff. The guys at NIST are about to publish a paper on this, which I've kind of seen a pre-release version of it, so it's not out there at the moment, but it's going to go in an edition of Safety Science at some point. This stair entry delay. So what they've got are cameras in the stairs, and they can work out when someone enters the stairs, and they can track reasonably well where those people are. But clearly there's a time it takes people to reach the stairs. And sometimes we might call this the pre-evacuation time. But really it's a combination of their pre-evacuation behaviour, the time it takes to decide to evacuate, plus there'll be some travel time from wherever they start on the floor to reach the stairs. So I'm going to call this the stair entry delay, and Garth's kind of using the same definition, because it's a combination of some travel time and some other behaviour, but we don't know what that is. What we know is at some point these people enter the stairs and they walk down the stairs and they come out at the bottom, and we've got some data that allows us to do something like this. So the guys at NIST have published this, but I'm going to criticise them a little bit here. All they did was publish a number like this, 224 plus or minus 146. And I'm going, well, what does that mean? Does that mean it's a normal distribution? What does this value actually mean? We'll come back to this. But this is the stuff that they've published so far. And they've got these big spreadsheets of information. So they've got details of every single occupant that they can track. So you've got occupant details, you've got their gender, you've got whether they're carrying a briefcase or a cup of coffee, you've got what coloured trousers they're wearing. I mean, some of this is like, who cares? But anyway, there's all this information about, goes down here, the spreadsheet goes on down, and if you've got 600 people, you've got 600 individuals where you know some information about them.
Did they interview them, or is it just on video?
It's just off videos.
Are there any mobility compared?
Some of the comments here might have something here, but I'd have to go and look through in a little bit more detail. The other thing they do try and track is the floor that the person entered and the floor that they were first seen. So because they haven't got a camera on every single level, they can only tell you when they first see a particular person, and I'd have to go back and ask them exactly how they worked out the floor that the person entered. You'll see sometimes the floor that they first seen has not been the same as the first one they entered. So if you've only got several cameras up and down your stairs, there are going to be people entering on levels you don't quite know where. So some of the spreadsheets have got quite a few holes in, where they don't really know what floor the person entered. All they know is where they first appear on a camera. And this causes some challenges when you try and model it, because you want if you wanted to model it in detail, you want to know where do they start, because otherwise, in terms of distributing your people around, you don't quite know where to start with. But anyway, the data is the data, and there's always a challenge. If you've got 62 stories of stairs, you just don't have 62 cameras, or probably the time and energy to process the data from 62 cameras. So there's a limited data set just because of the reality of doing these kinds of experiments. And then they've got this spreadsheet will go on this way, depending on the number of cameras and number of floors. They'll basically have the time that each person both entered the stairs and exited the stairs, because they can see the stair or the stair landing. They can see a person enter the stairs, landing, walk around the landing and exit, and they record all those times in a big column. And then for each set of stairs, if there's 10 sets of stairs, you'll have 10 columns of data. Of course, depending where that person started, they'll appear on one of the columns, and then you'll basically see that same person as they reach each stair level, what time they reached each stair level. So it's quite a comprehensive data set here, because we've got 6 buildings, 2 or 4 sets of stairs, and then hundreds of people in each case. So it's quite a large data set in terms of the ability to try and compare it with models. Another little criticism of it is the information they give about the geometry of the buildings is pretty limited. So they do give, so here's an image of the video camera. So this is all they've got in terms of a visual image, and they, as I said, they work out when a person comes down the stairs, crosses the green line, and when they cross the red line, and you've got that in your data set. In terms of the information, well, they have a bit of information about the width of the stairs. So we've got and the dimensions of the tread and riser. Now I need to put those things into my model, and those who've done the SFP calculations know that in the stairs there's a little formula that you can work out the speed of people going down the stairs based on the tread and riser. So I incorporate that formula. But then, in terms of some of the other details, it's really sort of limited. So they have this thing here that says, between floors 3 and 4, the stair configuration induces a horizontal transfer corridor. And I go, what does this mean? How long is it? How wide is it? I've got no idea. So at the moment, when I'm trying to model some of these things, I'm having to make a few guesses about what this means. So this is a little bit of a problem. Now, I only realised this about a couple of days before I was leaving this, and I was starting to work on this, and I went back to them and said, hey guys, I can't model this in detail because I don't really know what dimensions to put in. I managed for one building get this very detailed set of notes, which was a scrap of paper they kind of scribbled all over it. I gave them a real hard time saying, why is it all in inches? Hey, you guys at this, surely you should be using SI units.
So they're not inviting you back.
They thought that was fun. So for one building, I've got a little bit more detail about the dimensions. And for all the other buildings, I've had to make a few guesses at the moment. I've asked them really nicely. I've asked Rick Peacock, he said, oh, I've got all the dimensions, but he hasn't had time to get back to me and give me the dimensions. So I'm hoping I can encourage him next year to give me the dimensions, and I can actually do the modelling and kind of finalise it. But anyway, you work with what you've got. And again, Garth knows this sort of thing, that when you're asking, any of you guys, when you start asking other people for things, they're busy doing their things, and sometimes it takes them a while to get around to worrying about what you're doing. So when you rely on other people, you have to be aware that it can take some time. Oh well. So the question is how do we, in this network model, how might we model the stairs? And if we look at typical sets of stairs, we'll often have an intermediate or mid-level landing, and then we'll have the floor itself that people are entering the stairs, and we'll have two sets of stairs. So here's a nice diagram here that shows this. We have this mid-level landing, and we have the two sets of stairs. And so the question is, and it's again something that both kind of Garth brought up, and we've been sort of independently looking at this, which is quite useful. How might we model this? I mean, one of the advantages of supposedly this network model is that you don't need to get a CAD drawing and put all the details, which can be quite time consuming. One of the things that I'm trying to do is make it easy for the engineer to draw up the plans. But on the other hand, you don't want to make too many assumptions to the point where you're not getting results that are meaningful. So there's kind of a balance here. And part of this work is to look at, well, how complicated do we need to model the stairs to get reasonable results? So one way we can do this is to model each intermediate landing, or each landing as a node, like this, and each stair as a node as well, because each stair needs physical space for the people to stand. So we end up what I call the fine, myself and Garth are calling the fine network model, where we're modelling each component part of the stairs. The other way we might do this is what we're calling our coarse network model, and we basically just say, we'll add the two landings together and kind of have a double length landing, and says, well, the people are going to basically fill the same amount of space and they're going to travel the same distance, so why do we need to model both landings? And similarly with the stairs, we'll just assume that the two bits of stairs are like one long stair. Now clearly what we're missing out by doing this is any sort of things that might go on as people turn corners and the other sort of levels of detail. And do we need to go down to this level of detail, or is it okay to go with this coarser network, which halves the number or reduces the number of nodes and the calculations and probably makes it a little bit faster? Actually, I haven't tested the speed difference. So that's one of the things to look at. So basically, now I've got loads and loads of these things, which I won't show you all of them. But basically, what we're showing here is there's two things here. Firstly, is looking at whether we have a fine or a coarse network. So that's the across the scale. And the other thing I started looking at was, well, what time step to use. So this is similar to what you might do in a I suppose CFD model. You've got your kind of grid resolution, which I'm calling our node resolution, and how fine a time step to run the simulation. So basically here you can kind of look across, and I've got time steps. Now in the past I've been recommended 1 second time steps, and that stuff I did on the SFP handbook had a 1 second time step, and I got the results. I thought, oh, 1 second, that looks okay. But I've been looking at this in terms of reducing the time step and seeing what that does. So basically what we've got here on each of these charts, the black is the data from the spreadsheet. This is the people exiting the building as a function of time. So how many people we've got here? 160-something people. That's the dots from the spreadsheet. And the grey area is the results from the model, and they're the maximum and minimum values. So the grey area is, because I'm running it in Monte Carlo, we get a different run each time. This is 20 simulations, and it tells you the maximum and minimum. And certainly you can see here, if you look across by eye, you can see that using a finer time step, you get more of the dots on top of the grey. In other words, the model's working better, I suppose you could say. So that's one issue there. And also, you'll see that there is a difference in terms of whether you use a fine or a coarse network. But if you use it seems, at least from this data set, if you use a fine enough time step, whether you say this one or the 0.25 or the 0.1, the fact that you've got a coarse network no longer makes much difference. So it makes a difference here at the coarser time step, but as you reduce the time step, then the two models basically, by this data, give you effectively the same answer.